In a previous talk, in the first talk, we talked about the fact that clustering of data is a fact of life. It comes whenever there are nonlinear forces at work. There will be clustering. How often nonlinear forces are at work? Almost always. So non-clustering is an exception. Clustering is the commonplace situation. Human beings cluster. Children, when they play in a playground, play in clusters. If you are at a party, you'll see people will organize in clusters. Everything happens. Traffic moves in clusters. The emails that arrive at you comes clustered, bunched together. A wave of emails will come or messages will come, then there'll be a pause of silence. Another wave of them will come. So now the question is, what do we do with clusters? Why is it vital to find clusters? Because sometimes finding clusters can have profound implications. For example, if in some data space you have certain data variables with you, I'll take a variable with you. Let's say that you're looking at all 45-year-olds, and I'm going to oversimplify it. And what you do is you happen to notice that there are two clusters of people in a particular eye. One is the very healthy people, right? And one are relatively, and I'll just sort of oversimplify it, relatively needing a lot of medical attention. In the crowd that seems to be very healthy, you happen to notice that there are certain characteristics. They tend to exercise a lot every day, be moderate with their food, avoid the alcohol, perhaps, to a large extent. But in the other cluster, you see a behavior, a pattern of behavior. They're rather low on exercise and high on indulgence. So to find, therefore, to be able to see that these are two different clusters of people with two different kinds of behavior in a behavior space, they are separated out. Would you call that an insight, a medical insight? So in a word, would that give you an insight that perhaps the way to stay healthy is to belong to the healthy cluster? And to belong to the healthy cluster, you need to develop the habits of the healthy cluster. Are we together? That is the value. That's sort of a very immediate value that clustering brings. Now the question is, how do you find clusters in data? For two-dimensional data, it's sometimes obvious. Just visualize it, you'll see the clusters. Draw it out on a page, you'll see the clusters. On the other hand, if your data is not two-dimensional, and really is, three-dimensional, still you can rotate and see. What if it is high-dimensional data? And these days, data comes to us in very, very high-dimensional space. Let me give you an example of clustering, which I gave previously. I mentioned that one way that you could create as a news aggregator, automated news aggregator, you could create something like Google News feature, a simplified version, is what you do is you keep your ears to the ground for every single news site in the world, whatever articles they are publishing, small newspapers, big newspapers, whatever they are publishing, scrape it, and now project those news items into a vector space, into a word vector space. Right? What you will notice is that if something is important, a lot more people will talk about it, isn't it? So around that topic, around that, there will be a much more massive clustering of points, news items. Something that is of very low relevance, you will just find some local chatter about it. So if you search for the big clusters in the word space, and I have not defined the word space, I've deliberately been vague because text embedding space is a big topic. We cover it in our boot camps and our courses, but just take it as a hand-waving argument, as a text space or a language space. You would agree that if each article is a vector in a language space, a point in a language space, and two articles are talking about the same thing, they'll be pretty proximal in the language space. By detecting clusters, you can immediately tell the biggest clusters. You can tell what the breaking news is. And it is actually the technique that is used for this. The trouble is, those clusters are found, the language spaces are typically 300,000 dimensions big. Right? These are extremely high dimension spaces, unimaginably high. right? And now people have gone to 2 million, 3 million dimension spaces, 5 million dimension spaces, right? And they're doing these activities there. So we are not able to obviously visualize that. You cannot just project it onto the screen and say, aha, I see a cluster there. Right? But what you need is some algorithmic technique to discover those clusters. Right? So let us develop those algorithmic techniques. I'll start with the oldest one. It is called K nearest neighbor. But before I do that, I'll ask you a puzzle, a simple question. Why is it that clustering, which is so intuitive, why is it a machine learning exercise? Why can't we do? See, we do sorting of data. Sorting is a merge sort, bubble sort, right? We do it in our basic algorithmic classes. Why is it that something that seems to be intuitively even easier than sorting, clustering, observing, finding the clusters, at least in 2 dimensions, why is it a hard problem for machines? Why can't we just write a deterministic algorithm, right? Something that says, okay, yeah, this is it, right? Why should it be a hard problem at all? Can somebody guess? Just
There is
come up with
no
ideas.
there is no labeling to it, or we
That
can't.
is one way. I mean, see, the whole point is that labels don't exist. But if I put 2 heaps of sand, a human eye will immediately spot that there are 2 heaps of sand, isn't it? The sand particles are in 2 heaps, 2 clusters. But why? We look up at the sky and immediately we spot a cluster of stars, isn't it? Then why is it so hard for the machine to detect clusters? The reason for that is actually, it has to do with one man's cluster is not another man's cluster, right? In other words, see, when you see clusters, they're clusters within clusters. Imagine you see a big uh, galaxy of stars. Within the galaxy of stars, you will find subclusters. Within, for example, our own galaxy is a spiral galaxy, spiral, right? So it has the spiral arms, which are effectively clusters in their own right. Within that are again more clusters. Finally, you come to the solar system, and you could argue that the solar system itself is a small cluster of, right? A solar system by definition is a cluster of astronomical objects, isn't it? There'll be a star and there'll be some planets and rocks and going around it. So the definition of a cluster depends upon your perspective. Another way of saying it is that, see, when you look from a sufficiently large distance, you may see that, for example, you may look at a forest and you may declare that this entire territory, like you may say Alaska is forested. But when you zoom down, there may be clusters of forest, right? There may be areas that are sparse and areas that are dense, but from a distance, it looks like one giant forest, right? And so on and so forth. You can keep going to more and more finer resolutions, and you start seeing structures. So what are clusters? Is it that chunk of trees? Is it that whole region where lots of trees grow? Or is it the whole state of Alaska? You realize that, right? So there is a resolution question. That is why it's hard to have a deterministic algorithm to do that. That's one reason, actually. But it turns out we can prove that there is no deterministic algorithm. In fact, if somebody could find it, it would be at least NP hard to find such a, in the language of hardness of algorithms. So the way to solve it is not with deterministic algorithms, but using machine learning. So let's try some clever arguments to find clusters. Just like in regression, just like in classification, there is a very rich variety of algorithms to do clustering, right? And new clustering algorithms keep coming up all the time. If you're in a hurry to get a PhD in computer science, I highly recommend you pick up the topic of clustering and you can create one more clustering algorithm, right? Well, I'm just sort of joking, but it is that the field is fertile. People haven't exhausted the innovative ways that you can find clusters in data. But let's take the common ways that you can do that, and then I'll show it to you in code. I'm going to mention three. There are three core ways that I'll do it, and I'll just give you hand waving arguments. But the first one I'll work through in detail, and let's see if you get the idea. So let's say that let me pick a color that's more visible. So guys, when you look at this, what do you see in a very obvious way? How many clusters does your eye show you? Two clusters. But let us say we take the algorithmic approach. The first algorithm that we'll consider is called K means clustering. Cluster. So I'll just call it K means cluster or clustering. People write it differently. K means cluster is the more formal word, though people just call it clustering. It starts with this. It solves only half the problem. Whenever you have clusters, there are two questions involved. How many clusters are there? And what, where are they? Like, given a point, which of these clusters does it belong to? Is the membership question. So let me pose the two questions. A, how many questions? This is what the fundamental questions are. How many clusters? B, membership of each point to a cluster, right? Which cluster owns which point? You have to ask, isn't it? So now the k-means clustering answers only one part of it and does not answer the other question. It says, you tell me how many clusters you want to see, and I will show you that many clusters. So you notice that it has altogether bypassed the problem of resolution. It says it's your headache. You tell me how many clusters you want to see, and I will tell you who belongs to which cluster, which of those two. So let us take, consider k is equal to 2. Right? K is the number of clusters. We'll take 2. Then the question is, how does this algorithm work? It works in the simplest way that you can imagine. It almost feels like cheating. It says, just pick 2 points. So I could pick, which points would you guys like to pick? Let me deliberately pick. Okay, first time around, I'll pick 2 easy points. This point, A, and this point, B. Randomly pick 2 points, right? So let's say that I happen to pick these 2 points. Then assign to that point, consider them to be the cluster centers. Well, when you look at this and say, what are you saying? A and B don't look like the cluster centers at all. But machine doesn't know. It has just randomly picked 2 points. Now, for all the points which are closer to A, assign them to A. And all the points which are closer to B, assign them to B. So what will happen? A will end up owning all of these points, and B will end up owning all of these points. Is that true, guys? That is pretty obvious. And so let's write down the step. Initialization. Randomly pick 2 points and declare them to be centroids. In other words, centers of their respective clusters. B. Now step then. So let us call this the membership step. Assign each point to its nearest centroid. So you would agree that A will end up owning its own set of points and B will end up owning the second set of points. Then what you do is you go to the next step, which is called recenter, move the centroid. Now, in the cluster for A, find the center of gravity, the actual point, the point that is the center of it. Would you agree that that point would be somewhere here? Okay, would you agree that this pink points and this pink point would be the two new, I'll call them A prime and B prime, the new centroids, isn't it, guys? Repeat the process. Yeah, so you do this, and your job is to be in a cycle indefinitely till be in the cycle, be in this loop till the centroid stops moving too much. Too much is just to say that, sometimes it will buzz around a little bit from here to there. But once you know that you have stabilized, stop. So now what happens is I recentered and made it pink. And then I again do the membership. Now tell me, in the third step, I once again do the recentering. And when I do the recentering, where will the recentering be? Right there. Right there, isn't it? So this time the centroid didn't move much. So that's our terminal condition, isn't it? That is our terminal condition. As a terminal condition, I stop and I now declare we are done. So this was remarkably easy way to find clusters, isn't it? Now you declare all this to be one cluster and this to be the other cluster. That is it. All the points belong near the green dot to be Green's cluster, and all points next to the other green dot to be that cluster. Two clusters. We have discovered the clusters. We have done. Right? Now you can say, well, this was rather easy, but what if the situation was like this? So now I'll contrive a situation that's really terrible. A few terrible situations. So I'll try to redraw something that looks like essentially the same cluster. Is it looking more or less the same picture, guys? More or less, give or take. I'm not trying to pull a quick one on you. There we go. Now, let's just say that you happen chance make a terrible choice. You happen to pick, and let me blow this up. Let's look at this. Let us say that you happen to, by chance, pick two very close points as your clusters. This one and this one. Would you agree that these are rather terrible choice for cluster centers? Isn't it? And now what you do, you say, oh boy, let us do the membership. So you can convince yourself that if I draw the perpendicular bisector of this would be, all these points would be closer to A. And if I call this B, then all these points would be B, isn't it? But B would be actually more than that. B would be this cluster. B would end up owning all of these points, isn't it? Does this make sense, guys? Right.
But in first case, you draw the line very small, but why in this case?
Because think about all these points here on the right. Which of these are they closer to A or closer to B?
B.
To B. So B ends up owning those, isn't it?
But when you say closer to the point,
Euclidean distance, plain Euclidean distance.
That distance, is it something you configure? You say like this much points to the right, or?
Yeah. See, what happens is that because one of the first things you do in machine learning is somehow first convert the data to live in Euclidean space, so that there is a the simple notion of distance. Remember, Euclidean distance is d square is delta xi square, summation of this, right? In other words, in simple terms, it is x1, the x minus x prime. That's the way you're taught in school. For example, if you have 2 points, square plus y minus y prime squared is the distance squared, isn't it? That's the Euclidean distance, right? In higher dimension, it would be like that. So you impose, it is said that you can only cluster in metric spaces. Metric spaces are spaces by definition. And so now I'm using fancy mathematical word, but it's not actually that fancy. A metric space is a common sense space in which there is a notion of distance, right? But distance itself is a very precise. I would say that, what do you mean by notion of distance? What is distance? Yeah. Well, there are many kinds of distances, of which the most intuitive ones, there are two distances that most of us find very intuitive. One, the three distances that we find very intuitive. One is the Euclidean distance. It is as the bird flies, right? The other kind of distance is the taxi driver's distance. So in Manhattan, when the city is on a grid, unfortunately, the distance between 2 points, two intersections, is not through the buildings. It's not the straight line as the bird flies. You have to go along the streets, isn't it? That is called the taxi driver's distance. And you can always tell the bird reaches there quicker than the taxi does, right? Well, in Manhattan, even an ant reaches there faster than a taxi does, but that's a separate thing. Now, the other distance, the third kind of distance that we intuitively understand, is the cosine distance. See, when you look at the sky, you say, look at that star, and now look at that star. Near that star is, do you see that star? Right? Now, in reality, those two stars are not near each other. They may have vast distances to them. In fact, this star way back there may be closer to this star, right? In Euclidean sense. But when you look up at the sky, you're projecting all the stars to be sort of falling onto a dome, as though they are the same distance away from you, and you're looking at the angular distance between the stars. That is the cosine distance between points. One of the interesting paradoxes is when you do machine learning with me in a more intense way, it turns out that in higher dimensions, it is this cosine distance, angular distance, that is more effective than how the bird flies, the Euclidean distance. But the whole point of what distances are and what sort of things is a complete sub area of mathematics in itself and of machine learning in itself. It's about metric spaces and algorithms that are based on those. There are things like metric trees and whatnot in machine learning. We won't go there. At this moment, just use a common sense definition of distance, right? So you would agree that all points on the right-hand side, they belong to B for this, right? So, okay. So let's go with that. So now, what is the next step we need to do? Recentering, isn't it? We did the membership step. When we recenter, in this cluster, where does A center come out to be? Would you agree that this would be somewhere here? Right? Let me call this A. A has moved here, isn't it? A has moved here. What about B? B would have moved. Let's look at this. You have to find the center of gravity between all of these points. B would have moved, would it be fair to say, would have moved something like this, isn't it? Because these right points, they are pulling B towards itself. Would you agree? And so what would happen is, this would have taken a journey from here to here. Now let's again do the membership problem. What is A's membership? It will end up owning all the points on the left cluster, isn't it? And what is B's membership? It will end up owning all the points on the right cluster. Does that make sense, guys? Right? And now, once again, repeat yourself. Recenter. When you recenter now, would you say that your center will end up here, A, and for B, it would end up somewhere here, isn't it? 1 second, I'll take questions. Yeah, go ahead.
Doing the centering, are the humans doing?
No, machine is doing it. Algorithm is doing it. All it is doing is computing the distances and recentering. Membership, recentering, membership, recentering. That's all. And then now, from this third step, is there even a need to go to the fourth step? You do it once more. Let's pick another color. Which color should I pick? Let me pick, we haven't picked yellow for some reason. Time to go yellow. Okay. So would you agree that if you do one more recentering, you will basically be, okay guys, would it be fair to say that you will end up in that, basically this spot? This would be your next centroid, isn't it? And so has your center moved? Pretty much not moved. In fact, it's an exaggeration to say that it would move at all. Probably it wouldn't move at all. Right. So that, have you reached a terminal condition? You have, isn't it? And have you discovered your clusters? You have discovered your clusters. So remarkably, you notice that k-means clustering works, isn't it? And it's quite simple. Even in hard situations, it managed to find its way out. Not always. There are situations in which you can get totally screwed. For example, let us say happen chance, just happen chance. What happens is that, and I will now redraw the situation again, but I'll simplify it a little bit. You have these points and you have these points. And what you do is you happen to have pick 2 points, A and B, 1 and 2, such that this is problematic because now it goes. Now you can convince yourself that a reclustering of the data is not going to help you at all. You'll keep on sitting upon pretty bad clusters, isn't it? So when you get stuck in a situation like that, there are pathological steps. They're rare. There are 2 ways of dealing with it. See, one thing you can do with k-means clustering is try it again. Try 2 different random points, right? To pick another initialization point and see if you got better clusters. Maybe next time you're likely to get a better cluster, isn't it? So never run k-means clustering once, run it a couple of times. That's one way of doing it. If your data set sizes are small, then that is one way. But how would you know that if I do 3 trials of clustering, how would I know which of the clustering is the best? I need a measure. I need some way to judge. We had a way to judge regression. We had a way to judge classification. Now we need a way to judge this. So there are many ways of judging it, but one of the most common, there are many, many metrics, but a very common metric is this. It says, find every pairwise distance within the cluster. So see, when the clustering is good, do you realize that your pairwise distances are all small? Within the cluster, those distances are small, isn't it? Are we together, guys? Yes. So if you sum up all the pairwise distances, let me call this the case A, and this is the case B. And if I do xij, xj, between every pairwise distance within the cluster, what would happen to pairwise distances in this cluster, the bad one? Some distances will be small, but you realize that not this one. Some distances within the cluster will be astronomical, relatively, isn't it? Right? And so your distance, especially if you're looking at distance squared, those numbers would be, if you sum them up, they would be huge, right? That is why these are called sum squared distances within a cluster. So the sum squared distances in case B, and usually it's called, will be, actually let me use a color that is more visible, WSS of B, case B. I've used AB for cluster, so let me not use case A, case B. Let me call case P and case Q. How about that? Case P and case Q. Would you agree that case Q will be much greater than the within the cluster sum squared distance respect to the case P? Does that make sense, guys? Would you agree looking at these 2 pictures? It's obvious, right? The sum squared distance in the second cluster will be blown up. In the bad cluster will be blown up. Right. So that is a very common measure that is used. So what you do is you run the k-means a few times and you pick the trial in which you get the lowest WSS. You save the result and you pick that one. That is one thing you can do with clustering. Now, people have also suggested, now what in reality happens is sometimes data set sizes are huge, right? For example, Meta, Facebook, at one time used to cluster the whole social graph. Now, this was long ago. Obviously, today, graph theory, everything has evolved, but k-means clustering was used. Actually, even today, LinkedIn, all of them, social graphs have some clustering. So do you think they have the luxury of running a dozen trials when they have to cluster pretty much a data set containing most of humanity? It's not possible. It's not feasible, right? If these are big data clustering computes. Nevertheless, and especially because of that, you don't get a second chance. So people use some tricks. They know. See, they know the centroid from the last run. Reality wouldn't have changed too much. So you can start with those centroids. And the next time you go discover centroids in the new data, you start with what it was the previous times. That is a very sensible way. Then you don't have to run multiple times. The other thing that people do is, and then there are some heuristics that don't always work, but do sometimes work. So I'll just mention it to you. Suppose I have this cluster again, these two clusters again. What you do is pick a point. Let's say that you picked a point. Let me take this point. We picked that the last time, right? A. Then pick a point B, which is very far from A. So suppose I pick this point B. You realize that this algorithm will converge in far fewer steps. It will pretty quickly converge, right? So this is k-means clustering. It converges very, very well. It is the most popular algorithm for clustering of data. Its main limitation is, do you notice that most of my data points, they look rather spherical. They look globular, right? Like they're compact, they're convex in shape, right? So it's like you can wrap a balloon around it, shrink wrap them nicely, right? So my data doesn't look like, for example, suppose this were one cluster, this white was one cluster, and let us say that this was another cluster, and this was another cluster. You will realize that this, you can try it, do a mental experiment, and you'll realize that k-means clustering will fail here, right? Partly, it will be able to do this. If this was not there, this is the hard part. The snake is the hard part, right? It won't be able to get it. So it has some limitations. So now let's think, what other ideas can we do? I'll tell you an idea which is very physicist or physics inspired. It is called density-based clustering. And what it says is, look, guys, common sense. Clusters are places in the data where if each point you think of as having some mass, you're looking at high density regions, isn't it? You're literally looking at high density regions. So why not discover clusters using the intuition that clusters are regions of high density of points, right? Let each point have a mass, and then it becomes very, very clear. Yeah. Density is the number of points per unit volume. And you will see that, so the way the clustering, high density based clustering works, there are two particular algorithms, very powerful, that I'll introduce you to in this category, and we will do a bit of lab on them, rightly. And I don't think, there are many, many clustering algorithms, but I think I should stop at just two. So I'll tell you. But the first is called DB scan. It takes a bit of a formal approach that mathematicians would love. What mathematicians do is they take an axiomatic approach. They say, okay, I'm just having fun, right? And I'm going to cook up some notions and see if that helps, right? So they define the notion of epsilon neighborhood, right? What it means is, take a point A and draw around it a circle of epsilon radius. Well, mine doesn't quite look like a balanced circle, but let me try to balance it a little bit more. Bit better. Are we together? Then what you say is, if there is a point B, which is within your epsilon neighborhood, and let's take, there's a point C, and there is a point D. Let's see. Right? So does B fall, does any point fall within the epsilon neighborhood of A? B falls, right? So you say that A and B are directly reachable. and they create the word of direct reachability. Reachable. Now at B, let me cheat a little bit so that to bring home my point. So you realize that C is not within the neighborhood of A. Now you go to B and you draw a circle likewise in the epsilon neighborhood of B. Now in the epsilon neighborhood of B, you can say that B and C are also directly reachable. Together so far, they're directly reachable. And now what? What does it mean? And here is the fun part. Here is where it all begins to create a beautiful music. Now D is far from C. If you make the epsilon neighborhood of, when we look at this, you can say that D, if I just say, then I would say A and C are reachable. They are reachable using B. You can reach. Are we together? A and B are reachable. But D is totally not reachable. D is not reachable. Right? Now comes the beautiful, and now you say, what is all this math about reachability and games? But here's the beautiful thing. Believe it or not, we just discovered a powerful algorithm to find clusters. So let's go back to our cluster. Okay, suppose I take points that are, I'll just take fewer points. Now, this clustering algorithm says, randomly pick a point. Which point would you like to pick? Since we have been favoring the left points this time, let's favor a right point. Let's pick this point on the extreme right. Let's call it A and find every point that is reachable, which means either A, it is in the neighborhood of A, or in the neighborhood of a point through some links, right? So what will happen? A will end up owning, let's say, these many points, but these points will end up owning these many points, and these points will end up owning more points, and then these points will end up owning this, and soon A will end up owning through reachability the entire cluster. So now those points are off bounds. They belong to A. Now A cannot get any more points. Now you start with another point. What are you left with? You are left with, let's say B, all of these points. Let's say that you end up picking this point. You would agree that you'll end up owning the cluster, isn't it? And in fact, the beautiful thing about this algorithm is, suppose you have some random points here and there, right? They will belong to neither green nor to, let me call this B. And let's just say that you pick a random point. So now what happens? Let me call this C, D, E, F. Will C, D, E, and F have any clusters of their own? No. They will sit as isolate outliers. And considering that data has outliers, what we have discovered is an algorithm that is very intuitive, helps us find clusters, right? And while you are at it, also helps us find outliers. Outlier detection is very important in machine learning. That's how you detect fraud. That's how you detect anomalies, right? So this is a powerful algorithm that not only clusters, but detects anomalies and outliers in the data. That is the power of this algorithm. It's surprising how long it took to be discovered. It was discovered towards the turn of the century in the 1998, I would imagine. When this came about, if my recollection is right, quite literally, it was immediately granted the best paper in the machine learning field award for this simple idea, right? So this is one density-based clustering. There are other actually density-based clusterings, but in the paucity of time, I will not, when there is something called DENCLU, but let's skip it because that gets too much. Yeah, go ahead. Somebody
a quick question. So let's say you were to start a C, point C, the outlier point.
Yeah.
So if you start at the outlier point C, you find that there are no other points within the epsilon distance, and you are done. And what do you do next? Do you pick another point?
Yeah, you just declare C to be an outlier, then you try and look for another point.
Okay.
Right.
I see. So it doesn't get stuck, right? I mean, could it get stuck?
Yeah, you keep on doing this till you have exhausted all the points. Okay. So all the points either belong to a cluster or they are outliers.
Okay. Another question I had was about the previous algorithm, the k-means clustering algorithm. If you, let's say there are two clusters and you happen to select a value of k equal to 3. So would you then end up clustering it all incorrectly?
Yes. So that brings us the whole question of how do you know how many clusters there are? And I'll tell you a trick, but let's do it through the labs, through the code. Okay. When we look at real data, then I'll answer that question. I've deliberately held back that mystery.
How do you define this Euclidean distance epsilon?
As the bird flies. Euclidean distance is as the birds fly. The Euclidean distance between any 2 points is literally as the bird flies. The straight line distance, the shortest straight line distance. Well, again, I wouldn't use the word shortest. There's a reason I'm using the as the bird flies, because the shortest, they say beauty is in the eyes of the beholder. So is the distance. A taxi driver will completely disagree with you, right? Because to the taxi driver, he's still taking you by the shortest distance. It's just that he's constrained to the streets. Yeah. So that's a little bit tricky question, and I'm trying to be intuitive while still being mathematically precise.
Do you mean to say that we can choose some other distance other than Euclidean distance and get a totally different clustering?
Of course. So let me give you very, very obvious generalization of the taxi driver and the Euclidean distance, since you asked for it. So guys, remember, I didn't give it. You guys asked for it. So here it is. Suppose you have 2 points in n-dimensional space, right? Let's call the points x1 all the way to xn dimensions. So x belongs to n-dimensional space, and there is x prime, xn dimensional space, another 2 points, right? In some dimension. If it helps you, just think of Euclid, like simplify it to 2 dimensions. So x1, x2, and x1 prime, x2 prime. So you can draw it on a page. Here it is, x1, x2. Here is 1 point, x, and here is another prime, x prime, right? These are 2 points in this x1, x2 plane. Now, I'm going to do something funny. I'm saying x1 minus x1 prime, absolute distance, right? Plus x2 minus x2 prime, absolute distance, xn minus xn prime, the absolute distance, absolute value between the two, whatever the values are. This is your literally the taxi driver's distance, because the taxi driver goes right at the end of the street, straight line. This is the taxi driver's distance. Now I'm going to do, and this, by the way, I am saying raise it to the power n, right? And then take the nth root of it, nth square root of it. Now let's think about it. When n is equal to 1, it becomes the taxi driver's distance, right? Or Manhattan distance, as it is called. When n is equal to 2, it is the bird, as the bird flies, or Euclidean distance. This is the way Euclid defined distance. Isn't it, guys? X is equal to 2, n is equal to 2. Convince yourself that this is x1 minus x1 prime squared plus x2 minus x2 prime squared, for example. Square root is literally the definition of Euclid for distance, isn't it? But if I generalize it to n, this is called Minkowski distance. Minkowski distance of norm n. And in machine learning, believe it or not, we use L1 norm, L2 norm, L3 norm. So Minkowski distances are used. And in fact, where it gets even more creative, and that's why I was telling you, distances have a very interesting interpretation in machine learning. N can even be fractional. Nothing says it has to be 1, 2, 3, 4. It could be 0.5, 1.5, and so on and so forth. Are we together? Right? So this is just the most straightforward generalization of Euclidean distance. It's called the Minkowski distance. In machine learning, those of you, when you do it with me and you learn about a big topic, big topic called regularization. Big word, regularization. But what it basically means is you try very hard to convince the machine not to memorize the data, not to overfit to the data, right? But to actually learn to generalize from it. That's called regularization. So you bring all of these technologies in when you do regularization of the data. Are we together? Right? So anyway, Shankar, I suppose that gives you a flavor of how things go.
Thanks. Yeah.
It's fun. This subject is deeply fascinating because it intersects with mathematics, and mathematics is all such fun.
Yeah.
I hope you all agree with me.
It's very interesting because the 0.5 value for n and all those values, it's hard to even imagine what kind of a distance it is. It might give. It doesn't correspond to a physical distance, no?
No, I'll give you an intuition. See, when n is equal to 2, what is a circle? What a set of all points that are at the same distance from the origin they form a circle. But when you're looking at a taxi driver's distance, you can convince yourself that for n is equal to 1, it will be like a diamond, right?
Yes.
Because see, either you can go this distance up and then this distance, or you can go a little bit horizontally and a lot vertically. And like this,
Yes.
You can add up to 1, right, in different ways. So this is the taxi drivers, n is equal to 1. So the definition of a circle, which is that all points at the same distance from the origin, in the case of Manhattan distance, L1 norm, is actually, what is it? It's a cube, right? Then, and I will, do you want to go further? You will see that you will soon get notions like distances like this that take on this beautiful shape. And if you start increasing n for very large n, you will notice that you can convince yourself that for n is equal to infinity, this is what your circle will look like.
Wow.
So what you think of as this, and this is the utter beauty of mathematics, guys. And the fun of machine learning is in the underlying mathematics. The more you see it from a mathematical perspective, the easier you'll find the subject and the more fascinating you'll find the subject. So, all right, let's do some practicals, guys. I'll give you guys, it's already 8:40. I want to get to real practical labs. Let's give it a 10-minute break. So let us now look at the practical aspects. What does it all mean in real terms? We are going to look at a few data sets, and we'll try to apply clustering to it. So remember the old faithful geyser data that we met in regression? Right? Let's re-encounter that data set. I'll remind you that the eruptions, there are short eruptions and long eruptions. This data, doesn't it look something that we should cluster? One cluster will be the cluster of short, and one will be the cluster of long eruptions, right? So you can literally see that if you draw a histogram, this and this. Let's see how well k-means does. So now this is a point I want to make, and this is the mistake that people often do. You notice that when I do k-means, I am asking this machine to find for me clusters for all values of k from 1 to 10. Right? Because If you haven't seen the data, which is possible, how do you know that there are even two clusters? There may be just one big cluster of data, isn't it? So you take a number, upper bound, you first try it out with something, and if it doesn't work, then you go. So I took 1 to 10. So I'm going to do the k-means clustering 10 times, one for each clustering, right? Okay, why am I not able to? Yeah, so I'm saying I is equal to, so number of clusters is this one. Or find it. Now, when it says predict, it just fitting each point and telling the membership to the appropriate cluster. Then how do you know the quality of a cluster, guys? What was the measure we talked about? Within cluster sum squared distance, isn't it? So we compute that and we save it. We save that in an array. And why do we save that? We'll see in a moment. So look at this graph, guys. If you believe that there's only one cluster, then of course all the points will belong to that cluster, isn't it? If you believe that there are two clusters, has the machine done a reasonably good job? Two clusters has done a reasonably good job. If you insist that there are three clusters, then the machine will give you three clusters. Here it is. If you believe there are four clusters, here are the best four clusters. And so on and so forth, all the way to 10. Now the question is, if you could not visualize the data, if the data was in high dimension, how would you know how many clusters there are? What intrinsically makes the best sense for clustering? And so for that, there's a lovely technique, which I call the elbow technique, which actually not I, but the entire field calls the elbow technique. So can you spot the elbow in your hand? Or what is unique to it? That's where your hand bends, right? So what you do, the formal name is scree plot. So when you write your research paper, don't call it elbow plot, just call it scree plot. What you do is, on the x-axis, you put the number of guessed clusters. So say 1 cluster, 2 cluster, 3 cluster, right? And for each cluster, do you notice each number of clusters you computed the within cluster sum square distance? You saved it, right? You saw within cluster sum square distance is a measure of how tight that cluster is, isn't it? The smaller the number, the more tight it is. So you plot it out. Now you notice that if you believe there are only one cluster, the within that number is pretty high. It means that there's a lot of distances, big distances present in the cluster, isn't it? Now, reason through it logically. As you keep on increasing the number of clusters, soon you'll end up with very tiny clusters, right? And of course, the within cluster distances will be very small. And in the asymptotic limit, there will be 0 because each point will become its own cluster. So this curve, as you increase k, will of course go to 0 eventually. But you're not looking for that. What are you looking for? What can you see? The elbow. Do you see the elbow in the plot? When you see a distinct elbow in the plot, you basically say, beyond this, I'm reaching a point of diminishing returns. This is the right number of clusters, 2. So this elbow plot says there are 2 good clusters, and which of course is true. If you look at this, 2 good clusters, isn't it, guys? Right? So this is a very common technique and a simple technique, I'll say. Now, it has its plus and minuses, but consider this to be the most widely used technique for clustering, right? This is how you find clusters. Now, the same data, I will use the density-based clustering and analyze it. The same analysis, but use a different technique. And here it is with the density-based clustering. But observe, in density-based clustering, there is 2 hyperparameters. You consider a point to be within cluster if in its epsilon neighborhood, there are at least some other points. Otherwise, it's an outlier, right? So the minimum number of points that you want to be in the epsilon neighborhood of a point for it to be in belonging to a cluster is the hyperparameter of the model. In other words, you need to think how much should it be. The other is the radius of the neighborhood, right? So the epsilon value itself. So the problem with dbScan is based on what epsilon value you choose, you'll end up with different numbers of clusters once again, right? So in the first algorithm, K means clustering, K was the hyperparameter. You had to specify K. In the case of density-based scanning, you have to specify the radius, the epsilon, and the number of points, minimum number of points that must be there within that radius, right? So because of that, you get a set of different results. But once again, there are different measures you can use to find which are the best number of clusters. It says 2 cluster and 6 cluster. Let's see what 6 looks like. 4, 5, 6. Where is 6? No, not 6. No, it still claims that the number of clusters is always 2. The best values are still 2 clusters. So the density-based clustering is saying you get best clustering when you assume that there are only 2 clusters. Right? That's that. Now,
So where do you specify the distance, like you're saying?
the epsilon neighborhood.
No,
See, these are the radiuses. These are the epsilon.
In the first case, the previous.
K means clustering.
Yeah.
No, you don't specify distance. It just computes the Euclidean distance, right? Delta x, delta y square.
And these are all the libraries from the Python, the Panda, the k-means.
Okay, so since you asked, the k-means is there, dbscan is also there, but to get it so beautifully, you will realize that actually we have given you a lot of code, which is not so obvious. So there is a utility here somewhere that we have given you for this. So use that actually. Yeah, dbscan common. Do you see that density-based clustering? So there are all these utility functions that we have written that makes your life easy. Use a utility function because what comes built in with the open source is very low level. So you have to write a lot of code to get it right. So just use our functions and you'll be fine. Then it will become one-liners and two-liners for you. Right? So people have told me that sometimes they come just for the code. They register to a course just for the code. Yeah, go ahead.
Question on the density based, you mentioned the hyperparameters. How do you know those are the correct parameters?
No, you don't. That's a limitation of dbscan. And see, the only reason I stopped at dbscan is that it was easy to explain. I don't use dbscan. I use something called denclu, right? But it uses an argument called kernels. It's a kernel method. And gradient of kernels it uses. And it uses a hill climbing and so forth. So it gets mathsy. Then there are no hyperparameters. And it's also very scalable for high dimension data. So, but this is an introductory course. So we are staying with simple and easy to understand ones, which do have limitations, but at least we get a flavor of what clustering is. So let's look at another data set, blobs. If I call a data set blobs, can you imagine what it will look like? Blobs. Now look at this. This data set, the clusters are sort of rounded, right? They are like convex. So you would imagine, would k-means clustering work on it? It should work, right? It should work well. So it does. So you notice that, look at that. You just have to guess the right number of clusters and we will guess, but look at k is equal to 5, how well it does that. Look in the center where my mouse is. Isn't the clustering amazing here? Now, how do we determine that k is equal to 5 is the right number? Well, the problem is, which of these points has the strongest elbow? Well, 5 seems to have a very strong elbow, right? Here, this one doesn't have a strong elbow, this doesn't, this doesn't. This is the strongest elbow, right? So, like which has the greatest bend? Or the smallest angle between them. If two things are bent, the smaller the angle between them, the better. Right? So
this is also an algorithm in itself, finding the L.
Yes, the K. The K. And you use within the WSS, within cluster sum square distance. So it works well, but if you look at this, there seems to have been an elbow at 2. Isn't it? A little bit of an elbow at 2 and an elbow at 4. So let's go back and look what 4 clustering and 2 clustering look like. So look at this, 2 clustering, it says these two are one cluster and the yellows are another. Not very convincing, but okay. 4, okay, it says these two are one cluster, others are separate clusters. Right, it gets it wrong, but 5 is the strongest answer. Right? The same thing if you do with DB scan, then you will see that when you do it for different values of epsilon, or which value seems to give good answers? Well, if you look at this column, it seems to be pretty good, isn't it? Right, and also this one, these two, this seem to be doing pretty well. Let's see what the plot favors. The plot favors this, the data, the mathematical measures favors this, which happens to belong to which cluster? 5, right? To item number this, it says there are 5 clusters, and there we go, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, this is the one. This is the 10th one. So it says this is the best clustering. Would you agree that this is a pretty good clustering of the data? This is it. So this, there you go. So this is, but now let's take something hard. This is the data set again. I literally, this one I had to sit and hand create data point by point, and you'll see why. If this data set is called Smiley, and you can probably guess the reason why. Okay. Now, for this data set, let's see how k-means does. K-means, if I try for values of k is equal to 1 cluster to 16 cluster, are you happy with any one of them? Look at it more carefully. Are you happy with any clustering here? No, right? All of them get it wrong, isn't it? You happen to know that there are 1, 2, 3, 4, 5, 6 clusters, but when you look at k is equal to 6, it has gotten it wrong, isn't it? Especially the lips. It almost always gets the lips wrong, right? So what do we do? Let's see. Is there a clue that it would happen in the scree plot? Look at this. You notice that there are no pronounced elbows, right? Every single point looks okay, maybe not. It's hard to tell. Right? This is a classic sign that you may not have, you may be barking up the wrong tree, like you're using the wrong algorithm. Right? So what you do, when I use this with DB scan though, because DB scan is clustering based algorithm, look how well it does. Look, for example, at just the second plot itself, or the third plot or the fourth plot. Almost all of them get it right? All of these are getting it right. All these different values of the hyperparameter are getting it right. Would you agree? And that shows to you the strength of using a density-based algorithm. So guys, I'll stop here for clustering today. I hope there are many, the world of clustering has lots and lots of algorithms. Typically in elementary textbooks of machine learning, you find k-means clustering mentioned and something called hierarchical clustering mentioned. I deliberately left out hierarchical because by and large, it seems to have a same sort of limitations as k-means has, but it's a different approach. It is a different way to use it, and it has its own strengths and weaknesses. But I thought I'll choose density-based clustering just to show you a completely different approach to finding clusters in data. So guys, this code, my team is going to put again on the course portal pretty soon, or they must have already done it. I have, if I recall, you'll find it there. I hope you guys are having fun with this course. So now the question is, tomorrow is another topic, dimensionality reduction. Right?
So a quick question, Sif, before we go to on the clustering part, right? So to decide the hyperparameters, you are saying we need to plot either the scatter plot or the scree plot and then figure out by way of that, right? What if there are like n dimensions? Whatever we have seen is like only 2 dimensions, right?
No, but the scree plot is still a 2-dimensional. For example, for k-means, no matter how much your dimensional data is, the scree plot is still a 2-dimensional data, 2-dimensional plot. Right? You can use it. See, but you do bring up a point, which is that clustering doesn't have as good evaluation metrics as classification and regression has, right? So you have to use multiple measures. As a field, clustering is a harder problem actually. It is easier, more intuitive to understand, but its evaluation metrics are a little harder to come by. There are no perfect metrics. You have to try this or that and see what works. In reality, what happens is, see, you'll be working in some company which will be working in some vertical, let's say pharma or something. And from experience, people have figured out which of the algorithms works better for clustering their data. Right? For example, for pharma, they actually use hierarchical clustering quite a bit, which I didn't cover, and they also use density clustering. Right? So it depends from field to field. And they also say, okay, people will tell you, use this measure, we trust this measure from experience, right? Because the researchers would have found that in their field, this measure works better than that measure for clustering. So there's a lot of that tribal knowledge that floats around in this field. Yeah, go ahead.
Yeah, one quick question. You mentioned, pharma industry uses clustering.
Yeah.
What is a typical application? I mean, why would, so let's say you do all this clustering and you find a bunch of clusters. What do you do with it?
See, suppose you have a lot of biomarkers, right? And there's so many use cases are a bit hard to do. See, do you know the field of microarrays? Or you take a grid. So how many of you know what northern blotting, southern blots, etc., or running blots are? So, okay, what you do is you believe that this particular molecule may be effective for doing something, right? Work with this protein or something like that. You do some reaction you expect. Now, you can keep doing one particular compound at a time and see how it works or how effective it is. Or what you could do is you can take these days a much more mechanized approach. You can take a grid with little dots, right? And in each dot, they are all the same base material. It's a same germ or same protein or same something. And then you put different chemicals on all of them. And then you see what happens with that. When you get the data, because you have taken different concentrations of chemicals or different mixtures in a gradation, there is an XY axis there. Quite often the results that you see will show clusters. So it's getting, I know that this is getting technical. Okay, let me take a simpler example. See, when you look at biomarkers for diseases, quite often you find that certain biomarkers are clustered. For example, we know that diabetes is a metabolic disorder. So you will find that people who have diabetes, they don't have just one problem. They will have a whole cluster of problems. They will have thirst, they'll have frequent urination, they'll have sugar high, they'll have a tiredness, mental fog, many things will go together. And depending upon how you're doing the data analysis, when you project that data and all of the symptoms, you often start seeing that there's a granular nature of it. Like you will see that there's a big, let's say, I mean, this is probably not medically accurate, so this is all hand wavy. Let's say that you see a big cluster of people with metabolic disorder. Within that, you see a cluster, subcluster of people who are pre-diabetic. Here's a cluster of people with pronounced diabetic. Here's the cluster of people who are hopelessly diabetic, right? So you have clusters within clusters, right? When you have situations like that, then hierarchical clustering helps, because first you want to identify a big level differences, completely healthy versus predisposition to metabolic disorders. Within that, diabetes, pre-diabetes, etc., and so on and so forth. So biomedical research and pharma, they tend to use hierarchical clustering quite a lot. And in fact, they hang beautiful visualizations of what are called dendrograms on the wall of those hierarchical clusterings. You often visit the campus, you'll find especially in universities, you find some of these different kinds of hierarchical clusters being posted, put on a poster, because it makes it easy for people to remember. So I'm not, obviously, some other things that I may say, I just said, are probably somewhere in the neighborhood of being right. They are not absolutely right because I'm not a medical person, but that should give you a flavor of it.
Sure, thank you. Also, when we run k-means clustering, let's say we have n equals 100,000 points.
Yeah.
The time it takes is of the order of n square, whereas with DB, the other one which you mentioned, DB scan. Yeah, for that one.
Both of these are, see, k-means clustering for large data is still possible because there are various ways to accelerate k-means, right? Okay. There are lots of accelerated versions of k-means we do. That is where metric spaces that I was talking about comes. See, for example, and I'll give you the intuition behind it. Remember when we were doing k-means clustering, let me see. And I said that you decide which one, sometimes, entire blob of data will belong to one point. So you don't assign and check point by point, but entire regions of data you allocate to one particular centroid. It's somewhat like the way politics is fought, right? Okay, I get Texas and you get Pennsylvania or something like that, the way US does elections. So there are ways to accelerate k-means, and the DB scan, the way I showed it, is not scalable, which is why there are better algorithms. For example, Dentlu and many other density-based clusterings. In the open source community, very few of them have been contributed. DB scan is still there, but Dentlu we contributed that. We have a GitHub somewhere, I have to see. When you do the course, we make you implement Dentlu by hand. It works, and it's very scalable, because you can take a subsampling of the data and it will do the job. All right, guys, any other questions?
So, like, if the density algorithm seems so much like more versatile, right?
More?
Like, the density algorithm is like a lot more versatile, right? So
no, don't be. So the one person in the audience says, it seems that the density-based algorithm is more versatile. Shouldn't we always use it? That's what you are getting to.
Yeah.
The answer to that, no. In machine learning, there is a theorem. And remember, it's a mathematical theorem, so you can't argue with it. Right? It is that no free lunch theorem. It has a frivolous name, but it is perhaps the most important contribution that machine learning has made to the theory, AI has made to the theory of human knowledge. The no free lunch theorem. Actually, it's a group of theorems called no free lunch theorems. What it says is, no one algorithm is always superior than another algorithm. For some data, some algorithm will work better than other algorithms, specific areas, right? So with clustering, it's particularly true. It is the data that determines which algorithm will really hit the nail on the head.
So in which cases would k-means be better?
Most cases. See, k-means is your go-to. You start with k-means till you realize that it sucks for your problem. And then you go to something else. Right? Because it's easy, straightforward. Right? And then you realize when you visualize, you see, that is some of the techniques you'll learn tomorrow. And maybe let's keep data visualization for tomorrow as per schedule. When you do that, then you may get an intuition that the data is not globular. The clusters are not well separated out. That's when you start using other algorithms. See, the question often is, what is the purpose of finding clusters? If rough clusters are good enough, it's okay, it is not as good, but it serves your purpose. But if you really need to be precise, then you spend on hunting for the best algorithm.
So we have to use k-means on the entire population, right? We can't take a sample and run k-means on that.
See, people often do. Sometimes they will take a sample of the data, find the centroid, and after that, they will assign all the points to the nearest centroid. So they take a half measure approach, right? So there are all sorts of games that people play, and I have not gotten into the details. See, I have condensed an entire field where thousands of PhDs exist.
Sorry, apologies for all these. Yeah. Yes.
So come to the courses, guys. I mean, I'm not saying it to market my courses. I'm saying it simply because it's a beautiful subject. If you come, we'll do it more slowly and properly. This is just giving you a taste All right, guys. So if that is it, any more questions? We'll do dimensionality reduction tomorrow.